Good evening, everybody. Welcome to the Experience Swinton Astronomical Society. This evening, as you perhaps gathered, we have Kate Womack, who's presently studying at Hull University. Under an old friend of ours, Brad Gibson, who I'm sure keeps her on her toes.
Always.
So, she's a first-year PhD student researching in the field of galactic chemical evolution. She completed her undergraduate degree and Master of Science at the University of Hull, where she researched in the field of stellar nucleosynthesis. She regularly participates in outreach work to local schools and colleges to inspire the next generation of astrophysicist students. In her spare time, she's a Brownlee leader. She enjoys climbing and embroidery. I certainly mixed bag there without a doubt.
Yeah,
So can everybody please put their hands up and welcome Kate Womack.
Brilliant. Hi, everyone.
Brilliant. Right, I shall share this. Can everybody see that?
Perfect.
Brilliant. Okie dokie. So yes, as Steve gave that lovely introduction, my name is Kate. I'm a first year PhD student at the University of Hull. I'm really excited that you've asked me to speak to you all today on the stellar origins of the chemical elements. And this is a talk I like to give quite a lot. I've given it to a couple of astronomical societies already, and it seems to have gone down quite well. I thought I noticed someone from Cleethorpes Astronomical Society go by, added into the call. Apologies to that person because I am booked in to give a talk there next year and we'll be giving quite a similar presentation. So you're going to get some spoilers there, I think, but hopefully you enjoy it nonetheless. So yeah, I'll talk a little bit about the life cycle of a star, so the stages of life that a star has to go through, the types of elements that are going to be produced at each of those stages, and the processes that make them, why it's important for us to understand those processes. You know, why do we even care that stars make the elements that they do? What's it useful for? And then how we can actually go ahead and observe those elements. So lots of different things to cover. I don't plan on taking up too much of your time, probably the next half hour or so. So let's get cracking. As all interesting talks should start with these, which are some inspirational quote posters that I found on Pinterest. And it's that classic "We are made of star stuff" Carl Sagan quote. And though it has been totally cheesified, it's still entirely true. Everything that makes up everything around us started its life in a star. That's me, that's you, that's the chair you're sitting on, that's the laptop I'm talking to you through. Everything that makes up every object started its life in space. And I think there's a lot of things in astronomy and in astrophysics, as I'm sure you all know as astronomers, that can make you feel quite small if you think about it for too long. And this is the one that really does it for me. But before I talk to you about the chemical elements, I'll first talk to you a little bit more about the life cycle of a star, because I think it's important to know sort of the stages of life that a star will go through so you can understand the types of stars that are making these elements. And how a star evolved depends on its mass. And I've handily put that at the bottom of the screen so you can all see it. And you can see we've got sort of two main options for how a star might evolve. You've got the life of an average star. So this is a star between, say, 0.6 and 8 times the mass of the sun. So obviously our own sun is included in that track. And then you've got stars bigger than about 8 times the mass of the sun. But it doesn't really matter how massive a star ends up being. All stars will start their lives the same way, and that is as a stellar nebula. And so this is a cloud of very hot gas. And what will happen is gravity will pull that gas together and a star will form. And again, it doesn't matter the mass of that star. All stars will then begin their life on the main sequence. Now, when we talk about the main sequence, what we mean is that a star is burning hydrogen and making helium. that is how we characterize the main sequence portion of a star's life. It's after that main sequence that we start to see real differences in the way that a star sort of begins to evolve. So we'll start with the average star first. So if you're an average star, you'll finish your main sequence and then you'll become what we call a red giant. Now, the start of the red giant phase, you'll have an inert helium core. So the center of the star will be helium that's not really reacting, it's just sort of sitting there, surrounded by a hydrogen shell. And that hydrogen is still burning into helium. And as that hydrogen burns, it's going to exert a pressure onto the helium core, which causes the helium to start burning. And so then you've got a burning shell of hydrogen, a burning shell of helium, and in the center, a core of carbon and oxygen. Now, as that helium begins to burn and make the carbon and the oxygen, that begins to exert an outward pressure, which causes the layers of the star to expand outwards. And it's at that point you get what's called a planetary nebula. The name really is somewhat misleading. These sorts of things don't really go on to make planets. I think it stems from the fact that at one point we sort of thought they did, but it turns out they don't, but the name stuck around. And so what you have are these layers of gas around the outside and this bright core in the middle of carbon and oxygen. And eventually those layers will expand out so much that they're able to be swept away by stellar winds. And what you're left with is a white dwarf. So this is a white dwarf made up of carbon and oxygen. And that essentially is the end of life for a star of average mass. So then we'll look at the massive star. Now, a massive star will finish its main sequence and become what we call a red supergiant. Now, again, it'll start the same way, inert helium core, hydrogen around the outside. But once we get to the point where we have the carbon and oxygen core, we can continue to burn. And so we'll make things like neon and silicon, and we'll end up with a structure like this. And so this is what the inside of a red supergiant might look like. We call this sort of the onion shell structure, where you've got layers of different elements getting heavier the further you go into the interior of the star. So you can see we've got hydrogen, helium, carbon, neon, oxygen, silicon, and finally in the center, right in the core, iron. Now, I'll try not to get too nuclear physicsy with this talk because I realise you're probably more interested in the space stuff than the nuclear physics stuff. But I think it's worth mentioning that iron really is a stopping point when we talk about nuclear physics. And that's because it has something called maximum binding energy. And essentially what that means is if you take the centre of an iron atom and then the centre of another iron atom, so the two nuclei, and you try and fuse them together to make something heavier, you can't. There's too many protons here. So when you try and fuse them, they repel. It's like trying to stick two north poles of a magnet together. You know, you're not going to be able to do it. And so at that point, if you're not burning iron, you know, you're not generating the energy to be able to sustain the star. And so all of those outer layers will collapse in on themselves and form a supernova. And again, what happens after that supernova phase depends on its mass. So if you're sort of between 8 and 25 times the mass of the sun, you're going to end your life as a neutron star, you know, a really compact, dense ball of neutrons. If you're greater than about 25 times the mass of the sun, you're going to keep collapsing in on yourself and form a black hole. And so now I've talked to you a little bit about the life cycle that a star might go through. I think it's time to finally talk about the chemical elements. And I hope you're all familiar with this graphic from School of Science. This is the periodic table of the elements, but maybe coloured differently to how you've seen it before. So you can see that each element is given a colour based on the event or the type of star that makes it. So you can see you've got the hydrogen and the helium at the top from the Big Bang, not really a surprise. You can see that everything sort of up to and around iron is made in explosions exploding massive stars, and exploding white dwarfs. And then most of the things in the second half of the table, so from sort of strontium over at 38 to europium at 92, made in merging neutron stars and dying low mass stars. So you can kind of see where I'm going with this, right? There's sort of four main things to talk about. And I'll start with the explosions because explosions are cool. And I'll talk about exploding white dwarfs first. We call these type 1a supernova. And if you're paying attention, you might be sat there going, well, all of 2 minutes ago, you told me that the white dwarf was the end of life for an average star. So how can it then be exploding? Well, white dwarfs tend to occur in binary systems. So what you'll have is a white dwarf and its companion. And the white dwarf will use the force of its own gravity to pull material from the companion onto the white dwarf. And having this extra material added onto it causes the nuclear reactions to be able to start up again. And so then we're producing iron, we're producing what we call the iron group, so the elements between titanium and zinc. And eventually these white dwarfs will reach a critical mass, and we call that mass the Chandrasekhar limit. And that limit sits at about 1.4 times the mass of the sun. So once you hit over that amount of mass, that white dwarf will then explode as a type 1a supernova. Now, if we were able to be sort of a fly on the wall through the evolution of the whole galaxy, it would actually take quite a while for an event like this to occur. And that's because white dwarfs are very low mass, which means that they're quite long-lived stars. So you're looking at about 1 billion years or so before we actually see any of these type 1a supernova occurring. Whereas a much faster explosion of these, the exploding massive stars, are what we call core collapse supernova. And this is a type of supernova that probably springs to mind for you when you think of supernova. And it's the one I talked about earlier, where you sort of have all of those layers of elements collapsing in on itself. And these tend to happen with stars with a mass initially greater about 8 times the mass of the sun. Now, the reactions that take place with stars like this are extremely fast and they're very violent, which means these stars end up with very short lifetimes. We often say that these stars live fast and die young. And these stars make a lot of oxygen, they make a lot of alpha elements, and they make a little bit of iron. Now, an alpha element is any element that's made by taking one nucleus and adding a helium, because sometimes we call helium an alpha particle. Elements that are made in this way would be things like magnesium, silicon, things like that. So they're your sort of 2 main exploding scenarios. But you'll also notice that I still really haven't gone that much beyond talking about the production of iron. You know, and there's this whole second half of the table that I haven't even begun to talk about. And you'll also remember that I was talking earlier that iron is a stopping point when we talk about nuclear physics. So if we can't take 2 iron nuclei and fuse them together to make something heavier, how do we do it? Well, we need a neutron, because neutrons, as the name would suggest, are neutral. So this means if we add them to a nucleus, what we do is add mass. We can make something heavier without adding charge. And it's through this process, through neutron captures, that we're able to make the majority of this second half of the periodic table. And there are really 2 main processes for neutron captures. And I'll talk you through a little bit with them. Again, I'll try not to get too nuclear physicsy because I know it's not what you're here for, but sort of just to give you an idea of the different things that are happening. And I'll show you this. Now, this looks immediately pretty scary, but I promise it's not. Essentially, what I'm trying to show you is that there are 2 main ways that we capture neutrons. One is the S process, which stands for the slow neutron capture process. This means that we sort of start over here at zirconium-90, and we can slowly capture neutrons. When we reach zirconium-95, it's unstable, so we decay. we're at molybdenum. We capture some more, we decay again. And it just ever so slowly uses the low amount of neutrons that are available to build up heavier and heavier elements. Whereas your other option when you're using neutrons to make heavy elements is the R process, which stands for the rapid neutron capture process. And this requires lots of energy and lots of neutrons. So you have to imagine you've got all of these neutrons in the system. And what basically happens is it kind of goes, wow, okay, we've got lots of neutrons here. Let's make loads and loads and loads of heavy things. And once we've run out, we'll decay them all back to something stable. And that's as much nuclear physics as I'll go into. You'll hardly hear any more nuclear physics for the rest of the talk, I promise. And you'll notice what I've done is handily color code these two processes to correspond with the two remaining things I've left to talk about. So you'll notice that the S process is mainly occurring in dying low mass stars and the R process in major neutron stars. So we'll talk about low mass dying stars first. Now, low mass dying stars are also called AGB stars. This stands for asymptotic giant branch. Essentially what that means is a star has reached its red giant phase and it's formed what we call an intershell region. So this is a region within the inside of the star where more complicated nuclear reactions tend to happen. And within that intershell region, the S process occurs. And it's the S process that makes things like strontium, yttrium, zirconium, barium. All of these sorts of elements are made in this way. And these stars have a range of masses, which means they have a range of lifetimes. But what we really care about is that they're able to make those S process elements. So I'll move on and talk about the major neutron stars. And so this is sort of our main postulated site for the R process. And neutron stars are very compact, very dense balls of neutrons, about 20 kilometers in diameter. And if you've got a neutron star major, what you've got is two neutron stars orbiting around each other and slowly getting closer and closer together. And eventually they will merge. And these mergers are very highly energetic. You know, it's just the sort of thing we would want for an R process event. And we were struggling for a long time, really, to come up with a site for the R process because of how energetic it is. And when we got that detection by LIGO of the neutron star mergers, not only was it really important for people who care about gravitational waves, it was also really important for people like me who care about the production of the elements, because that confirmed that major neutron stars are definitely there, and you know that they're able to produce that europium, the platinum, the gold, those elements that we really needed a good site for their production. And so I think, you know, without going into too much of the nitty-gritty of the nuclear physics, I've given you an explanation of sort of the sites that are producing most of this periodic table. So I'll give you a quick recap of that. So how are the elements made? Well, the elements are made via nuclear reactions in the interior of stars. And different reactions can occur depending on the mass, how metal rich the star is, the temperature, the density of the star. Lots of different things play a role in exactly which nuclear reactions and how much of those nuclear reactions can take place. And computer modeling is really useful to help us understand how those reactions take place. And I'm really lucky to be an astrophysicist interested in this field at the time that I am, because our computer models are pretty good in getting better and better all the time. You know, so I'm able to take this computer code that my colleagues use, give it a temperature, a density, a mass, an initial composition. So initially, how much of each element does that star have? And I can follow its evolution through time. I can see how much of each element a star will have as it goes through its life. And that's incredible for me, and it's a really useful tool for science. But I sort of want to draw your attention a little bit to how we studied the production of the elements and the synthesis of the elements before all of this. and talk about this paper. Now, this is a paper affectionately known in the community as Bsquared H. And this was a paper written in 1957 by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. 2 B's, an F, and an H. It's not difficult to figure out where the name came from. And this is a really, really fundamental paper for people who do what I do in sort of nuclear astrophysics, chemical evolution. And this is because, obviously in 1957, we didn't have the advanced computer models that we have now, but they were able to use what they knew about our closest star, the sun, and what they knew about the nuclear physics experiments that were happening on Earth to come up with 8 processes that they thought were occurring inside of stars. And most of these processes turned out to be correct. I think out of the 8 they came up with, 7 pretty much dead on, which is incredibly impressive. And they did that just with their knowledge of the sun and Earth-based nuclear physics, which blows my mind every time. And if you ever want to go on a bit of a Wikipedia deep dive, sort of look up somebody interesting, Margaret Burbidge, if you haven't heard of her, is incredible. Definitely worth a Google and a look at as a person. Fabulous pioneer for women in the field. And I'll stop fangirling now and talk about science again. And you can see that this is sort of the main figure from this paper. And you can see they have a peak at iron because of that stopping point. They came up with the R and the S process I talked about before. You know, they really did a wonderful, wonderful job. But why is it so important to understand where these elements are produced, you know, how they're produced and the stars that make them? Well, it's important because of galactic chemical evolution, which is the field of study that I work in now for my PhD. And although it sounds like sort of a scary term, it essentially does what it says on the tin. You know, it takes a model of the galaxy and says, well, how has the galaxy evolved chemically through time? How has the carbon evolved? How has the nitrogen evolved? How has the argon, the cobalt, you know, all the different elements, how have they evolved from the birth of the galaxy until now? And so what we do with galactic chemical evolution is we compare models of the evolution of the galaxy to observations of stars, which is what this figure on the right is showing. So the black line is a computer model and all the coloured points are observations of the stars themselves. And where we have a really good match, so where the black line fits the coloured points really well. So for example, with oxygen, we know that we've done a good job. We know that our model is able to take what we know about, you know, when the stars form, when they die, what do they eject, and do a pretty good job of reproducing the oxygen that we observe. Whereas if you look at something like scandium, so that's SC on the right-hand side, we don't do a very good job at all. You know, the model is sitting down at the bottom and the observations are much higher up. So that tells us that actually there's probably something missing in our knowledge. You know, we're not thinking about the evolution of scandium in the right way. Perhaps, you know, we're missing a whole population of stars that can produce a lot of scandium. You know, perhaps we've not thought about the nuclear reactions properly. So this helps us get a picture of how the galaxy has evolved through time. And so obviously, if galactic chemical evolution is so important, we need to make sure that we're getting good observations of stars. So how do we get those observations? How do we observe the chemical elements on the surface of a star? Well, we use something called stellar spectroscopy. Now, spectroscopy takes the electromagnetic radiation from stars, so that's visible, that's UV, X-ray, infrared, radio, and makes an absorption spectrum. And this spectrum can be used to figure out which elements are present on the surface of a star. And I think this schematic on the right-hand side sort of explains it quite nicely. I'm hoping you can see my cursor, but if you can't, I'll try and sort of talk through each thing. We can see it, brilliant. Okay, so you can see that you've got this sort of section of the night sky and it's picked out the target star, the one we want to take the observations of. So we take all this light from the night sky and we can filter it out. And that light will pass through the plate and hit a grating. Now, hopefully some of you might remember from school physics that when light hits a grating at an angle, it can split into its component wavelengths. So you can see we've got the blue light and the red light being split. Think Pink Floyd sort of thing. And it hits that detector. Now, if we were sort of doing this here on Earth, we might expect that absorption spectrum on the right to be totally complete, you know, no gaps from blue to red. But what you'll notice is that there are gaps, there are wavelengths that are missing. And this is because different elements can actually absorb light at different wavelengths. So if we know, for example, the wavelength of light that carbon absorbs, and then we see that it's missing from our absorption spectrum, then we know that there is carbon present on the surface of that star. And that is how we take those observations. And we take those observations using spectrographs. You know, to do spectroscopy, we use spectrographs. And you have two main options, really, as you do for most sorts of telescopes. You have a space-based spectrograph and a ground-based spectrograph. Now, a space-based spectrograph, and that's getting harder and harder to say, would be something like the Hubble telescope. You know, there's a spectrograph on board Hubble telescope. Obviously, as it scans through the sky, it's taking those observations of the stars. Or your option for a ground-based telescope would be something like the Very Large Telescope in Chile. And there's actually plenty of spectrographs at the Very Large Telescope. Some of them focusing on specific wavelengths, some of them focusing on specific regions of the sky. But as I'm sure you'll know, as ground-based astronomers, there's lots of difficulties to observing from Earth. You know, you've got weather conditions to contend with. And also the atmosphere actually absorbs a certain wavelength of light and also distorts the wavelengths of light. So we have to make corrections for that when we're doing our analyses. So actually, if we can, it's much more beneficial to use these space-based spectrographs. And I'm pretty sure there'll be a spectrograph on the James Webb Telescope, should it ever get off the ground. And this is also the point when I talk to astronomical societies where I have to make a confession, which is, here is me talking about telescopes, but my research doesn't use one. Unfortunately, I'm not particularly an observer. However, for my master's research, I actually used a whole population of stars and their abundances, which was data collected from the Hubble Space Telescope. So even though, you know, I wasn't the one, you know, sort of taking that raw data and doing the analysis from the telescope itself, everyone in astrophysics is impacted by the data the telescopes provide. But I always have to make that confession because I wouldn't want to parade myself around as, you know, a telescope user when really I'm not. And the last thing I'll talk about is how these elements get to Earth. You know, I started by saying we are all made of star stuff. You know, everything around us came from space. But how did it get here? And you sort of have three main options. The first is it was around in the nebula that the Earth was born in. It was essentially baked in as the Earth was born. And this is because, you know, our solar system is roughly 4.5 billion years old. The universe as a whole, about 13 billion years old. So you've got 9.5 billion years to play with there in the interim, where stars were born, stars died, they made those elements and released them out into their galaxies and into the universe. And when it came time for the Milky Way and our own solar system to form, the gas that was around was enriched with all of the elements from stars that had previously died. And we were able to take those elements and sort of bake them into the Earth, really. They were there in the rock and the gas and the dust that formed the Earth. The second option is meteors. Now, the picture of the meteor that I've got is actually a picture of the one that landed on someone's driveway in Gloucestershire back in March, if anybody remembers that. And And so meteors, again, are formed out of the rock and the gas and the dust that's in space because of those stars dying. You know, there are dust grains within those meteors that have come from stars exploding and stars dying nearby. And obviously, if you think about the amount of meteor landings over the last 4.5 billion years, it's going to have brought a good amount of chemical elements with it. And meteors are not only useful for sort of enriching the earth with these elements, but they're also very useful for us as scientists. And this is because we can take those meteors back to a lab and we can analyze those dust grains. We can look at the chemical elements that we observe, and we can sort of infer where that dust might have come from. So if we see a specific ratio of carbon-12 isotope to carbon-13 isotope, you know, we might be able to say that that particular dust grain was formed because of an AGB star. You know, we can start to use those grains to infer things about the dust in that meteor. And the last thing to talk about is winds. Now, if you imagine you've just had this huge core collapse supernova, you know, this star has collapsed in on itself and exploded and released all that material. That material is going to get carried on stellar winds all the way eventually to Earth. And again, if you think about the history, the sort of 4.5 billion years or so, a fair amount of the chemical elements are going to have found their way to us because of winds in space. So there are three main ways really that the elements get here. And I told you it'd be a fairly short talk. I don't want to ramble on. So that is the end of everything I've got to say. So I'll thank you all for listening. I hope you enjoyed it. I hope that maybe you learned something, or if you didn't, I hope at least it was interesting. And yeah, I'll take some of your questions.
Thank you, Kate.
Brilliant.
That was a really enjoyable talk, and you finally, in my mind, sorted out the slow and rapid methods of building atoms. So could I ask you to stop sharing your screen?
Yep, absolutely.
Hopefully it stopped sharing easier than it started. Has that disappeared?
That's lovely. And
Brilliant.
So, ladies and gents, as usual, questions. I'd prefer a digital hand, but if you can't raise a digital hand, wave at the screen. Give me a few moments. I'm going to worry Kate now, because you've broken our local record, Kate, with 56 connections, and I think we've got several doubles as well. So congratulations on that.
Oh, well, thank you.
So, ladies and gentlemen, digital hands, please, for questions. Looking around. Oh, Peter, New Zealand.
Yeah, from the other side of the world. Very nice talk. Thank you. Just, you know, when you model.
Oh, bother. Sorry, Peter. That was my fault. Could you just unmute yourself and start again?
That's okay. So very nice talk. Thank you.
Thank you.
When you model these elements, of course, a lot of nuclear data has to get into it. And you probably know the international attempt at the moment to produce more accurate nuclear data in order to more accurate for the accurate simulation of the isotope distribution, which we have at the moment at certain places in our universe. But this is often not very easy, because nuclear physics is no easy task. At the moment, they are more on a what I call a semi-empirical level, because you cannot really go down to the interaction of the quarks, and that creates all the difficulties producing nuclear data. But you also have excited nuclear states involved.
Yes.
In these, for example, R processes, and so the task is over the next, I would say, 10 years to really get going, producing more accurate nuclear data, which you can then feed into your program. So are you using certain databases? Are they updated all the time, or what is going in your program in fact?
So for the sort of nuclear synthesis code that we use, it's reaction rates, I think, from the Codonis database. In terms of my galactic chemical evolution code, We just tend to use the most up-to-date yields we can find for the things that we want to do, really. I mean, exactly as you say, it's all about finding sort of the most up-to-date, the most complete sort of set of things that you can find. I'm not sure in terms of the nucleosynthesis code how regularly the Codonis database is updated, and then as a secondary, how often then our code is updated to reflect those reaction rates. But I think when we sort of compare the models that we have for the nucleosynthesis to stellar observations, for the most part, it does an okay job. It depends what element you're looking at, but we seem to get fairly decent agreement.
Okay, Peter.
Yeah, thank you. And the other thing is, you probably know about the long-standing controversy about the supernova explosion versus neutron star mergers, but I think that has been now more or less settled, right?
Yeah,
I think most of the field now is probably leaning towards the fact that the site for the R process is neutron star mergers, right? But I mean, I suppose there's always a case for different weird types of supernova and like different mechanisms of explosion potentially also doing that.
Okay, thank you, Peter. Got a question from Neil Allen. Are there neutron star massive star collisions? And if so, what range of elements would be produced?
okay. A question that
I'm not sure I have the answer to be honest. If there is sort of a neutron star massive star merger, it's not something I've sort of read about. The production of the R process and sort of neutron star mergers isn't particularly my area. I would imagine if it were possible and if it did occur, it would be sort of R process elements. It would probably be things, again, like the europium, the platinum, the gold, stuff like that. But again, not entirely my area, so I wouldn't want to sort of say for certain.
Do you know, you astrophysicists are getting to start to sound like historians. That's not my era. That's what I always get when I talk to historians. That's not my era.
this is the trouble though with
I think a lot of the time with getting sort of researchers like me to give talks like this is a lot of the time you end up finding your niche really quite quickly. So I could tell you a lot about like one specific element or one specific process, but then having in-depth knowledge sometimes of some of the others is difficult, and you get a question like that and you're going, oh, I wish I knew. And I know my exact colleague who would know the answer.
Well, maybe he'll give us a talk. Right, Gary from Mid-Kent.
Yeah, hi everyone. Hi Kate, thanks for a really interesting talk. I wanted to ask you, back on your periodic table slide, there were a couple of pink boxes and a couple of grey boxes.
yes.
I wondered if you could just how it looks like only two of beryllium and boron have got cosmic fusion as their source, but the grey ones weren't mentioned at all. What was the reason for that? I just wondered if you could just highlight the pink ones and what the grey ones are about.
Absolutely. Okay, so the
Pink ones I think was probably lithium, beryllium and boron. And the reason really that we leave these alone is because they're made by something called spallation. And so this is where you have sort of radiation that interacts with carbon, nitrogen and oxygen, and it makes those elements through spallation. It's not something particularly well understood, and lithium is a huge problem for us as people interested in the chemical elements. You know, it's something that we don't really seem to produce enough of.
Yeah.
So they're the pink ones. The grey ones are grey because there are no stable isotopes of these elements. I think it's technetium and I can't remember off the top of my head what the other one is.
Protactinium, was it?
Promethium?
Something like that, promethium perhaps. Yeah, so essentially there are no stable isotopes of this element. And so we don't say that we do make them obviously in stars, but obviously they're going to decay. So we don't get any sort of stable. But I like to talk about this because technetium is quite interesting. because technecium we can make in the S process. And one of the isotopes of technecium, which is technetium-99, actually is so long-lived that sometimes we're able to observe it on the surface of a star. So if we observe technetium-99, we know that there is active S process happening in that star, because obviously it has to decay at some point. So if we observe it, we know that the S process is happening at the time that we observe it, which is awesome and one of the reasons why technetium is really cool. I gave a talk a couple of weeks ago here in Hull at the Hull and East Riding Astronomical Society, and there were a couple of people who I think were sort of previously in the medical professional, medical technicians and things like that, and they were saying they can also use isotopes of technecium for medical imaging. So not only is it cool for me from a sort of astrophysics point of view, it's also actually useful in sort of our everyday lives.
Oh, well, thanks anyway, because you've rekindled my interest in the periodic table. I haven't seen it for many years.
Okay, thank you, Gary. I've
Thanks.
got a question from Irene. Can you tell how many generations a star has gone through by its composition?
Yes. So this goes back to the idea of
Galactic chemical evolution. So you have to imagine after the Big Bang, what you have is hydrogen and a little bit of helium. So then the first stars that are going to be formed are going to be made purely out of hydrogen and a little bit of helium. Those stars explode and that'll mainly produce things sort of from core collapse supernova, so things like magnesium, silicon, stuff like that. So then the gas is now enriched with hydrogen, helium, oxygen, carbon, magnesium, silicon. So the next generation of stars is formed with that little bit more material. There's little more elements. And then those stars go through their birth, they make more and more heavier elements, they die. And then that gas becomes further enriched with a different set of elements. So I guess it's maybe a little difficult to always tell how many stellar generations a star has gone through, you know, before that star was born. But for example, you can sort of tell how metal poor it is. So we use a ratio of iron over hydrogen. And if that ratio is quite low, we know it's quite metal poor, which means it was probably born before lots of heavy elements were sort of enriched, were sort of thrown out into the gas. So we probably can't tell exactly, but we can give a good estimate of sort of roughly when it was formed based on how much metal, how much iron versus hydrogen it has. I hope that answers the question.
Okay, well, if Irene's back with us, I know that she had to leave for a moment. Maybe she could just ask a follow-up. I've got off top, well, not off topic really, from Becky from Mid-Kent. She sent them a question. It's about studying. And so she's hoping for a little bit of direction. She says, thank you for the talk, Kate. Really, really interesting. How did you decide on this area of study? I'm currently studying at college and I'm currently applying to university to complete a space science degree, but I find myself stuck on which direction to go. I'm really enjoying chemistry. We are currently learning about covalent bonding, which I'm enjoying. So I think Becky needs a little bit of direction.
Yeah, absolutely.
So I'll start with how I decided on physics, which, to be honest, I think I sort of always kind of knew that was the direction I was going to go down. I always liked science. I was always interested in sort of how things worked. You know, I would sit and build Lego with my dad, and, you know, we'd watch programs about bridges being built and stuff like that. You know, I was kind of interested in that sort of thing. So I always knew that I was probably going to go down the physics path. In terms of once I actually got to my physics degree, how did I decide to go sort of in the chemical evolution, astrophysicsy sort of direction? To be honest, I think if you know you want to do that space science degree, that's a really amazing step. tick, you know, you've nailed that, you've got sort of that kind of direction. Don't worry so much about the kind of what the next thing is after that. You know, I didn't really know the direction I wanted to go down. I didn't even know if I really wanted to do a PhD. You know, it was always in the back of my mind, but I couldn't even fathom what I would pick to study. And actually it was a case of when it came to picking my undergraduate dissertation topic, you know, the staff members came out with a list of different projects, different things they'd like people to study. And my supervisor for my undergraduate project had something about the synthesis of the heavy elements using the eye process, was the title of the project. And I'd never really seen that before. You know, it wasn't something I knew a lot about. And I went to speak to him about it, and I just thought, yeah, this is for me. This is what I'm really interested in. So don't worry about, you know, knowing too much exactly what it is you want to look at, what it is you want to narrow down to. You know, go and enjoy your space science degree, go and enjoy that process, and what you find interesting will fall out of it eventually, don't worry.
I think that's very good advice, Kate. And Becky, go and do the space science degree and go and do some observing. Go look down a telescope. It's really good fun. I'm going to ask Catherine. Catherine, can you unmute yourself, please? And can we have your question?
Yes. If you use your spectroscopy and to look at supernovae, have any elements of an atomic number equal to or greater than 104 been picked up? And if they have, could you determine if they're in the island of stability?
Could you repeat that question, please, Catherine?
Sorry.
Okay, by looking at your using spectroscopy and looking at supernovae,
Okay.
have any elements with an atomic number equal to or greater than 104 been picked up? And if so, could you determine like if they're in the island of stability?
Greater than 104. None of these isotopes will be stable. The heaviest stable element that we have is lead. We have isotopes of thorium and uranium that are quasi-stable. So we say they're essentially stable because they live quite a long time. So in terms of actually detecting these elements using spectroscopy, I'm not entirely sure. I imagine they'll be quite short-lived and decay pretty fast. Again, not entirely my area, so I wouldn't want to say that we haven't, but I would imagine it's not super likely.
I can jump in if you wish. That's
Go
exactly
for it,
my
go for it,
that's
yeah.
exactly my area.
Yeah, go for
Okay.
it.
So I mean the other probably more stable isotope is plutonium, because sometimes you find often entries like in Wikipedia that uranium is the last stable element. That's not quite correct. But when you go beyond plutonium, you go into the so-called instability of, they call it the sea of instability. And there was, of course, another sea of stability predicted at around 114 or 116 or 126. They are still arguing about this. But these elements are extremely short-lived. So even if you have more neutrons inside, you are now perhaps in the second range, maybe minute range if you are lucky. And so, yes, they have been synthesized in neutron star mergers, but extremely short-lived. And to observe them in outer space would be extremely difficult and a challenge.
Okay, Catherine.
Thank you.
Thank you, Peter. Peter Lloyd.
Yes, thank you, Paul. Thank you, Kate, for a fascinating talk. I was actually particularly interested in the nuclear physics part of your talk. Probably comes from my ancient history as a chemist, when I often wonder where the elements came from. I just wanted to ask you about the formation of the elements between cobalt and rubidium. According to your periodic table, they're made in much the same way as the lighter elements. And I just wondered whether that meant that they were made by successive neutron capture from iron, or whether they're formed in some other sort of nuclear merging way.
You're exactly right. So
those elements are formed majority via neutron capture, so onto iron to make those heavier elements. But rather than doing so in the dying low mass stars and the major neutron stars, we do those neutron captures in the exploding massive stars and a little bit with the exploding white dwarfs as well. So you do get a little bit of the neutron captures going on in those types of stars too.
So they're not formed in the cores of smaller stars. The iron, it definitely stops at iron. You don't get neutron capture going on there.
Yeah, so the fusion
Path really tends to stop at iron, teensy bit of cobalt, and then after that, it's neutron captures that do that.
And that's done in the explosions.
Yes.
Yeah. Okay. Thank you.
Okay, thank you, Peter. Just a follow-up from Irene with her question earlier about generations of stars. So are there some stars that are still born with the lighter elements, or are all areas of the universe seeded with the heavier elements now?
Again, a good question. So at this point, obviously, we've gone
through many different stellar generations. So any stars that were to be born now would be enriched with, the gas that would be around would be enriched with essentially a little bit of everything. It's still mostly going to be hydrogen and helium, just because, you know, they are the most dominant elements that we have. But yes, most of the stars that are born now will have sort of a little bit of all of the heavier things kind of sprinkled in there. But we're talking very small quantities, you know, hydrogen and helium are still the most dominant elements that we have.
Okay. Right, ladies and gents, I'm looking around for any last questions. I've not got any hands up, and I'm not seeing anybody waving at me.
There's a Neil Allen with a question.
We've got one on.
Oh, sorry, Neil.
Yeah, sorry, I did put it in the chat, but on the graphs that you showed about the observed against the theoretical, from my screen, it looked as though nitrogen and potassium also the observed were quite a long way from the black lines.
Yeah.
So can you give us some idea about why that is?
Yeah, sure. So the figure is a little bit old.
I think it's from about 2006. And so obviously in the interim, we have improved our knowledge of the production of both of these elements. Sometimes the other thing to say is there's lots of different aspects that go into a model of chemical evolution. You know, you've got to consider how many stars are made, how many of each different types of star are made, the gas that's coming into and out of the galaxy, the gas that's moving around the galaxy, the amount of each element that's made by each star. You know, there's lots of different parameters to consider. And sometimes it's just a case of that particular model is just not so good at reproducing the nitrogen and the potassium. You know, perhaps it was made because we want to study a bit more the heavier elements, for example. Sometimes, like for example, the model that I use, pretty decent at producing fluorine, not so great at reproducing cerium. It's just one of the things we have to tackle, is it's difficult to get everything right in a model. I'm not sure about that particular model that was used, but I imagine it is just a case of the input parameters that they put in. And if you were to use different input parameters, you might get something different. This is why it's so difficult to get an accurate model of the chemical evolution of the galaxy.
Okay, Neil.
Yeah, thanks. Great.
Okay. And I think we're going to make this our final question. Ian Hargreaves from Mid-Kent.
Hi there. Sorry I was late coming on. Computer played up. But a very interesting talk, Kate, for the last 3/4 of it that I managed to catch. I just wondered, you know, is there ever going to come a time, you know, eons and eons in the future, when there isn't any hydrogen and helium left around?
Good question.
And if so, would we then, would any proto star have to collapse a lot more to start the fusion reaction off? And could it do that?
My immediate feeling
On if we'll ever run out of the hydrogen and helium, probably not. I think there's probably more sort of imminent death of the universe things that are probably likely to happen before that ever did. Well, not death of the universe, but sort of kind of big events and galaxy mergers and things that are going on. I mean, perhaps, but I think the universe will be a bit too cold and expanded for anyone to really care at that point. Yeah, I think that's probably the best answer I can give to that.
Okay, thank you.
Okay, so I think that just leaves us to give Kate a big Mexborough Swinton Astronomical Society. Thank you, Kate, for an entertaining evening. Thank you very much.
Thank you for having me. Thank you so much.